Thank you very much, Olivier, for the kind introduction. Appreciate it. So I prepared this presentation with having the fact in mind that people attending the seminar might not be necessarily doing research in energy systems, so they could come from all sorts of backgrounds in OR, operation research. So I start from some kind of introductory stuff, which could look trivial to people doing research in energy systems, but they are necessary to basically provide the backbone for making the case. And as the title says, most of the keywords you see in the title are kind of familiar. And the thing that might be of need to be a bit explained is that what does it mean by highlighting community or urban aspect and highlighting hybrid aspect. So these two things, I will provide some background, and then I will have presentation of few basically works that we've done in my research group with the help of PhD students, MSc students, related to this topic. And there were reasons for selecting those because it shows a variety of basically models in there. So without further ado, I'm going to be providing a background on what do I mean, or what is the concept of urban community renewable energy. And I'm looking into hybrid solutions, so how these two are kind of in parallel with each other. And I will be looking at basically from where optimization coming to the picture and what sort of dimensions or aspects we're looking at them when we're trying to build optimization models. So looking at investment financing, locationing or location analysis, decisions about the scale, configuration and sizing. Sizing is different than scale. Scale means if it's done at the building level or community or city level, and sizing would be the capacity basically of the technologies that we are equipping. And then, of course, would be the operational considerations. So how things are going to be scheduled, controlled. And then I will also mention things about asset management, because these technologies are there to last for quite some time. So we need to have some strategies in place to extend their life expectancy and minimize basically their any need to replacements, and minimize the risk of failure as well. And at the end, I will provide 3 case studies and 3 modeling efforts that we've done at my group, highlighting highlighting the optimization model developed. So looking into objective functions, decision variables, how the model is constructed. And I'm going to also highlight from what sort of data analytics is being used into enriching the optimization models. So looking at this picture is kind of ideal picture of what we can call urban community renewable energy, which is showing that there are many distributed points of generating heat or electricity or cooling capacities with renewable energy dispersed across a wider geography. And then we do have energy storage capabilities to make best use of renewables. So I will later discuss the fact why energy storage is always something necessary hand in hand with renewable energy. Okay, so would be networks or distribution networks to provide electricity, to provide heat, and to provide cooling. Why we're looking at, so what are the main characteristics of urban community renewable energy? The first characteristics is that we're dealing with several sourcing points. So could be one technology like solar panels, but many of them, or could be varied technologies basically. So having wind, solar, geothermal. So that means we do have choices, and we do have a kind of these technologies joining forces to face the energy load. We do have technology network exchanges. So as we need to, we are incorporating a multitude of technologies. Each one of them would be a point that are interacting with the distribution network. Distribution networks that providing power, electricity, heating, cooling. And in some places of such a network, there could be needs for exchange with the grid, and there would be needs for exchange with energy storage capabilities, and there would be a need to exchange with networks or distribution systems that are providing fossil fuels as kind of backup. So natural gas, diesel, this sort of things. As such, we do need a lot of coordination. So what technologies are there, how they're connected, and many of kind of decisions of what is in and what is connected, what is disconnected. And that would be presenting a kind of complex system in order to design, in order to operate and manage in long term. Why we're opting for it, so why bother doing this? There are certain benefits. So economic benefits, first of all, something that comes to the mind is the economy of scale, because we're talking about larger scale and focusing on incorporating as many as renewable technologies in. So increasing the scale of production and diversifying it basically is one of the economic benefits. So the scale, when the economy of scale improves, we can bring down the unit cost, and that the cost that is passed to the consumers in form of prices, we would be able to provide more competitive prices for the users. And when we deal with larger scale renewable energy incorporation, we would be able to employ larger scale energy storage. So when energy storage, the technologies that we are incorporating are larger and larger, again, the unit cost is going down, and improvement of economy of scale we're going to have. And the other aspect that also contributes to improvement of the economy of scale is this sort of collective coordination of demand. So all the time you would be having the option of opting for the cheaper options rather than for the expensive one, because you have a variety of options to tap into. So at any point of time where the decision is getting made to see what productions are in, what productions are off, and how the users are connected to points of energy production, we could opt for the cheaper options if we have the choice. Beside this economy of scale improvement, another economic benefit would be having less and less investment in new grids. And so infrastructure build up, we're going to have savings, we're going to be deferring them, we're going to be delaying them. And as the localized distributed capacities could compensate some of this kind of infrastructure build up for future. The other benefit, we look at it, and for some places, especially communities in the north that are off-grid, is resilience, which means that you're not only relying on one source. So if that source is off, you don't have access to electricity, you don't have access to heat. Diversifying the sources would improve the resiliency. And in that respect, when the system is connected to grid, it's the case of urban communities, there could be exchange with the grid. So when there is shortage, there could be purchases from the grid. When there is surplus, it could be the other way around, and we would be able to sell to the grid. In the case of off-grid, so that capability would be added alongside energy storage and alongside existing fossil fuels. And that with that, you would be using fossil fuels less and less, and they become kind of backup capacities. And that is especially the case for remote communities which are off any sort of grid, power grids, or even natural gas networks. With all those benefits, there would be challenges. And these challenges, some of them are because of the nature of renewable energies. Some renewable energies are intermittent, which means when we talk about solar energy or wind energy, in certain points of time, we do have a lot of solar radiation, so we could generate a lot of solar energy. In some other times, we are less fortunate to have enough solar radiation, and the generation is going to go down. And that doesn't mean that when the generation is high, the demand is also high. And when the generation is low, the demand is also low. Sometimes it's the reverse. Okay, so at the times that, in the middle of summer, which we do have a lot of basically renewable energy, but then when you look at the electricity consumption and load, it's much lower compared to the winter time, which we use a lot of electricity and energy for heating the spaces. So that intermittency creates a kind of situation that sometimes you have surplus, sometimes you have shortage, and it's not easily predictable. The other issue is the scale. So when we opt for community urban scale renewable energy, you have to look into connecting many users to many technologies, and you also have different layers of the power, heating, cooling loads to be satisfied. So that scale is the root cause of many complexities, and you have to be in a situation to coordinate everything. Otherwise, every single issue in such systems could create domino effect and migrate to other users, migrate to other technologies, and then the whole system is jeopardized. The challenges with respect to operation is that coming from the nature and scale into the operation, so as kind of inputs. So when we are making decisions to charge or discharge energy storage capabilities, so that needs to be done with respect to something that is expected real time and near real time or near future, because charging is coming with a lag. It takes time for charging to take place, and it takes time for discharging to take place. So it cannot be at kind of any instance of time, especially if the energy storage technology is of a kind of mechanical nature, like thermal energy storage or compressed air energy storage. In that respect, understanding what is going on now and maybe in few hours from now and even day ahead is critical into making such decisions and scheduling the connection of technology. So at what point of time we are connecting solar panels to the energy storage, at what point of time the wind is connected, wind sources are connected, and how this sort of many decisions that needs to be taken care of is coordinated across the system. And the last challenge, so among the main challenges of urban community scale renewable energy, is the discrepancy between design and operation. So the scale is big, the operation is complex, and when we design something, it could become quickly obsolete when we do have many more users joining the network, so the population is going up, the load demand is changing, and there is always a lag between updating the design in order to catch up with the changes at the operation. So this discrepancy leads to having most of the time kind of undersized energy storage or undersized renewable energy technologies in place. And most of the time at the beginning, when we start operating such system, we're going to have a kind of situation that many things are going to be oversized. So you have to spend a lot of money, a big amount of capex to generate design things that could last, let's say, for the next 5, 10, 15 years, best case. And at some point, you're going to go into the undersized, territory. Okay. At the core of urban community scale renewable energies, we do have the concept of hybrid solutions, which means we're not relying on one technology, we're relying on multiple technologies. And that is on the side of production. So we might have renewable energies that are kind of varying and are of intermittent nature, like solar and wind, or the ones that are kind of more reliable and steady, like geothermal biomass, as well as a multitude of energy storage technologies. So batteries cannot be the only solution to promote, because usually batteries, the drawback is with the scale. So you could increase the scale of batteries to some point, and after that, it creates a lot of space requirements, and then speeding of the degradation of the batteries when the sizes are getting bigger and bigger. So we need to opt into other types of energy storage, especially if we talk about heating supply and we talk about cooling supply, which is not directly, can be supplied directly by batteries. Okay, so that brings thermal energy storage. That brings air-based systems. So basically, compressed air energy storage system. The principle is that when you compress the air, so you could store the energy in the compressed air. And once you release it, so you allow for the expansion, the energy is going to be released, and that could be used for in a turbine to generate electricity. In that respect, so that might be one of the last slides in terms of background. When we talk about hybridization, hybrid solution is not only about sources of energy. It's not like saying I have wind and solar combined. There could be combinations with fossil fuels as well as backup. There could be combinations with more kind of a stable renewable energy like geothermal biomass. And on the storage side, we also look into diversifying, because as I mentioned before, when you increase the scale, you improve the economy of the scale. And also when you have diverse distributed systems around, you enhance the resiliency, because if one system is off, the others can catch up and kind of compensate. Okay. Now, after the background, I'm looking into the optimization. So what is the contribution of optimization? What type of optimization models we could have for the urban scale, community scale, renewable energy systems? The first aspect, and some of these models could address many of these aspects, but I'm looking into dimensions. Basically, what is the focus of the optimization? It could be only at the investment financing. When we talk about urban community scale, in many practices, we do have diversified investment. So you not only see public sector, you see private sector coming in. Even the consumers, even what we call them prosumers, basically, they could be willing to contribute. So in that respect, governance would be an issue. So who owns what sort of partnerships are there, what sort of contracts are there, who is in role of management, what are the rules for the membership. So if the user, so later on I will discuss that, how the pricing is managed. Is it following the market prices? Is it following some sort of adjustments, or is it a kind of fixed price for the duration of the membership? And what would be the role of any carbon savings in providing competitive pricing? Who is paying for capital costs? Who is paying for operational costs? So how this cash flow is managed, basically. And if there are returns, if there are revenues, in which way these revenues are collected, how they are distributed, how consumers, going to be receiving share of this revenues if there is involvement of exchange with the grid. But as we see it, it's done collectively. And the other thing with respect to investment and financing, how to optimize, how to make decision, is the way the users are participating. So a user is joining this network and become a member, but that when you become a member, you have to use whatever this collective system is providing for you, or you individually have the right to switch off and connect to the grid. So you could basically exchange with the grid yourself, or it needs to be done collectively. And so that brings if the usage is a requirement, or you have the choice between, so the having basically no mandate to tap into this, and you could opt to do it, or if you have to be member, if you're a member, you have to use it basically. So that also would be a kind of at the individual user's perspective, a decision that needs to be made based on the prices, especially in places that the electricity is kind of decentralized and you have choices, you're receiving choices from distribution companies, and at the also management scale, so knowing how many are joining, how many are present, how many are connected, and how many of them are under the requirement membership, how many of them are kind of having the choice, and this affects the way things are managed. From optimization perspective, there is also things about location and scale, because renewable, some of the, so like when we talk about wind and solar, the availability of wind and solar resources are not the same everywhere. So we do have, maps for Canada telling us what are the basically potentials of solar radiation and potentials of wind speed. And if you move toward places that might have more of kind of sun exposure, you might be compromising on wind. And at the end, it needs to be, if you're trying to bring both location in, both technologies in, the candidate locations, the community that is chosen, the building that is chosen for a sort of practice, the decision about it will change. So where would be the best location to implement such thing? What would be the ideal communities to look for? And even in case of more stable renewable energy sources like geothermal, the potentials are varying, and that is highly depends on the extent of conductivity at the soil level. So there are places that have more active, basically, soil layers and high degrees of soil conductivity, which means you could exploit more energy from within the ground. And in some places, there is not much such potential. So you might have geothermal, but you have basically limitations or caps in terms of how much you could bring it in and switch it on. So those things affects where which one of communities choosing what type of technologies. And would be decisions and optimization decisions in terms of the coverage. So if we're doing it, we are doing it at the building scale. So the parameters, the objective functions would be toward the user and their basically payoffs in terms of being exchanging with the grid and benefiting from renewables. When it goes to the community, and that means we are trying to preserve kind of shared resources, and demand profiles and loads needs to be controlled. So we cannot have some users that are going to the maximum in terms of heat, and some users being suffered because of having a shortage in terms of heat supply. Okay, so that coordination needs to be done. And when it comes to the urban scale, the main question would be how to integrate with the main grid, and how to not only when we do have dispersed capacities, how different buildings in the city would benefit, and how we could make sure that there is a fair basically distribution of resources and benefits toward citizens. Going into kind of more engineering type optimizations, we do have decisions to make in terms of configuration and sizing. So what technologies to choose, at what capacity, and that needs to be in line with the profiling of the load, so what is energy demand. And even if you select the technologies, you're coming up with the capacities, how they are going to be connected. So what are the flows between these technologies, energy flows between these technologies? So this is system design. And that kind of going to be a kind of back and forth decision between selecting the technology and connecting them through the system and then defining the capacities. So efficiency of all these technologies has a factor, and potentials of those renewable energies has a factor. And with that, once this is done, you might say so the optimal solution, which you're trying to minimize a cost, most of the time whole life cost, and minimize shortages or loss of power, you're going to end up with a set of technologies from renewables, fossil fuels, energy storage, and some sort of configuration for the distribution of electricity, heat, and cooling, and responding to heating and cooling demand. Going into the operation, so the main challenge or the main reason we build optimization models is that we want to make decisions for any moment, but then run the system for a year, or 2 years, 3 years, 15 years. Okay, so there are going to be two types of decisions that kind of are real-time, near real-time nature, with long-term, short-term, and long-term consequences. So that is about scheduling. So at any point of time, which energy storage technology is receiving the power, doing the storage? Which technology is discharged? Which basically, how much surplus is sold to the grid? How much is purchased from the grid? In what areas we have shortages? And we're going to have many of kind of binary integer type decisions. So the technologies that are member of the system is going to be connecting, disconnecting to this system all over time, depending on the needs. So when there is a need, they're going to be called in, and when there is no need, they're going to be off. And same as to the energy storage. I mentioned that before, when we talk about energy storage, there is always lag in terms of charging, discharging. So scheduling decisions to benefit from the energy storage needs to be done ahead of time. So you cannot expect energy charge, discharge on a real-time basis to be used, basically. So it takes some time, and that creates a lag. Sometimes this lag is short in case of batteries. Sometimes this lag is long in terms of mechanical systems. And of course, when we do scheduling, control, and operational planning, one of the main characteristics that we need to preserve is the critical load. So whatever shortages happen, there is a minimum of load that needs to be preserved because it's dealing with some critical capacity. So if electricity is supplied for water treatment, if electricity is supplied for the basically heating some buildings that are of critical nature, or the cooling, let's say we talk about the data center that needs cooling, okay? So this is critical load, because if that load is not provided, data center needs to shut down and the internet is going to go off. Okay, so it's going to be creating domino effects for other systems, and that is critical load, a minimum load that under any circumstances we need to preserve. Last would be about asset management. So we want to have these technologies, these networks of heating, cooling, power supply lasting for some time, because there's been money, there's been investment in there, and we want to preserve them for longer time in order to make sure that we don't need to build new capacities. We don't need to, we can save on building new grid. And with that, there needs to be combinations of effort to maximize life expectancy and minimize cost of service life while maximizing life expectancy. And that is where data analytics coming in, because it's all about future and the scenarios that we're going to have. At the core of it would be prediction of failure at the component level, at the system level, and so what is the risk? What is the magnitude of the risk? What is the likelihood of this risk? How we can minimize it for the overall system, considering all the components, and how the maintenance needs to be scheduled in order to make sure you're not under-maintaining or over-maintaining this system. Because either way, if you under-maintain, that is a risk to reliability. You're going to have shutdown, and if you over-maintain, that means excessive cost. And if there is a need to replacement, if there is a need to expansion, let's say more consumers are joining, population is growing, how it is going to be done, what technologies, from what angle the expansion is going to be done. So that is a kind of less than 30-minute overview of how optimization models are making sense and used in case of L1 community scale renewable energy. Now I'm going to provide a couple of case studies or couple of few research that we've done in my team to just dig a bit into the technical details and make sense of all the background I've provided so far. Please, if at any point of time, I should have mentioned that at the beginning, if you have any question, you could stop me. So you don't need to stay up to the end. And of course, at the end, I will open up the floor for the questions. So ask questions at any point of time. You could raise hand. The first piece of research I'm talking about is basically what the goal is to look at urban buildings, and this is done at the building scale. So at a specific building, and bringing in solar panels, integrating into the building, and trying to offset some of the energy loads by these solar panels. The modeling is aiming at doing the optimal sizing, so capacities, and optimal scheduling, considering the seasonal changes in the demand profile. And with two additional aspects. The additional aspect is that we're looking into resilience, which means we want to preserve two aspects, which I'm going to talk about them later on. One would be, both of them going to be related to a critical load somehow, and how we want to make sure that this integration is not going to jeopardize reliability and resilience of energy supply for this building. So that is one aspect. And the other thing is to use a combination of energy storage systems. So a kind of hybrid energy storage system with batteries, electrical system, and compressed air energy storage as a mechanical system. Okay. The reason doing it, because for the compressed air energy storage, you could go for a bigger scale. We're talking about compressing air. You could go for a massive air tank, and any time that you do charging and discharging, you could store big amount of energy. Whereas with the batteries, there is limitation in terms of how much electricity could be shared and what sizes of batteries are needed. So, and thinking of the fact that batteries at the end of the day are electrical, if something happens to them, we do have a kind of backup storage, which is the mechanical. Okay. Looking into this, so I mentioned the problem is optimal sizing operation of building integrated PV with hybrid energy storage system for with the goal, additional goal of resilience assessment. The way the model is formulated, the problem is formulated, is a bi-level mixed integer linear programming problem. Level 1, sizing is done, so it's more about capex, what is to be built, and the level 2, which is kind of exchanging with level 1, is the operational decisions. Okay, so based on the capacities are built, operations are triggered, and based on the requirements at the operations, there would be feedback for the sizing. So these two problems basically communicate with each other. Decision variables at the level 1, it's more about capacity, number of PVs, capacity of battery, capacity of compressed air, which has compressor and turbine. And we also have things about capacity of mechanical energy storage system. I forget that this study also has a thermal energy storage system. So 3 types of energy storage systems, and the TES thermal energy storage is for the heating supply, basically. So, and at the level 2, which is the scheduling operations, we talk about the main thing would be charging, discharging of this energy storage capacity while we are responding to the load. Just an overview of the objective function. So level 1, we do have annualized levelized cost of energy, which means total cost divided by the amount of energy expected to be generated. So the amount of energy expected to be generated is coming from the operational model. And based on the capacities in the level 1, we're going to have constraints in the level 2. So whatever operation you're going to have is going to be constrained by the decision in the decision space of the level 1. Okay, so level 1 receiving input from level 2, and level 2 is constrained by what is happening in level. Okay, so I'm not going to go through the solution approach, etc., because it would be basically out of scope for a short presentation. But the constraints we do have, as mentioned, all sorts of capacity, a constraint with respect to technologies, supply and demand, heat balance, power balance, electricity balance, energy balance, basically. And additionally, in the phase 2, we do have 2 constraints to take care of resilience. One is the curtailment constraint, and the other one is resiliency constraint. Curtailment is okay, so the way we define it is coming from intermittent nature of renewables. So we want to maximize the benefit from renewable energy inputs. So if we do have a lot of energy generated by renewable energy, but that energy is not used in the system, so we do have a lot of surplus, and we cannot sell it to the grid because grid has some limitation in terms of how much you could sell to it. Sorry. And then you could not store it because all the batteries, all the storage capacities are full. So you're going to be experiencing a situation that you have a surplus that is of no use. We want to minimize that sort of situations, okay? So we're going to put or reduce the number of times situations that we have such a thing. So we put a constraint on the amount of curtailment during the operation. So with the data analytics that we are providing it from demand profile and solar radiation and wind speed, so all these predictions for future, we're going to build up scenarios for future and then see a constraint that's going to take care of how much solar energy can be generated, okay, to make sure that we don't end up with no use energy. And then there is the resiliency constraint, which is about percentage of time we're going to be experiencing shortage. So it is called loss of power supply, okay? So there is demand, but this demand is unmet, okay? So percentage of time that we have that situations, we're going to bring it to a minimum. It cannot be 0 because there could be moments that we absolutely need to switch to grid, but there are the moments that we don't need to switch to grid, okay? So we want to minimize that sort of shortage. Even if we switch to grid, we might end up with shortage because, you know, at the time we want to buy from the grid, it's not enough basically access for us there. So there would be the loss of power percentage would be the time that we need to trigger some saving strategy. So we have to shut down certain things because we're not going to be making the load, okay? We want to put a constraint there to bring this to a small percentage of time. Okay, so looking at the results, so this is, so it is done. The optimization is generating daily solutions. So the one on the left is a solution for a winter day, and the one on the right is a solution for a summer day. So the yellow one is the basically what we see it as production of solar energy, and the weightings, how much load we had unmet, how much surplus we had. So we didn't have any surplus in the winter, but there are surpluses in the summer. And then in terms of unmet load, the summer ones are mostly shifted. We could manage to shift it mostly toward the nighttime, and where there is limited need for cooling. Okay, so for every single day, something like this could be envisioned from the optimal solution. And the black lines is the profile. So the profile is predicted through data analytics. So we're looking into the historical trends of the building, and then based on that, using some machine learning approaches, we build up a kind of demand profile for specific days during the year. And here is the two parameters that we will be observing: the curtailment, trying to keep it under a limit. And when most of the curtailment, you see it's happening during the summertime, which we have a lot of, it is expected to see that, but we managed to keep it under a certain percentage. And also loss of power supply, as you could see, the instances that we have shortage are mostly happening toward the end of the year. So this figure is showing from January to December, basically. So toward December and end of November, December, with a lot of heating needs, we need to trigger some saving strategies because we're going to have shortages there. Okay. Quickly, this one, the second one is the case of hybridization when we have wind and solar energy together. So we want to benefit from wind capacities and we want to benefit from solar capacities, and doing it at the community scale with a specific type of energy storage, which is the compressed air energy storage. The reason we chose that one because it could be a large scale energy storage system. So you could store something for the quantities for the whole community, basically. So in that case, the problem was formulated as a Markov decision process. So the way we're looking at it, it's the scheduling problem, and we're looking at it as whatever happening at this point of time would be the reason to would be providing the basis for the transition to the next stage. So we see the planning and the scheduling as a kind of transition in place. Okay, so based on what is the amount of solar radiation, what is the amount of wind speed, what is the amount of load at this point, we make decisions for the next period. So, and this is done hourly basis. So on a kind of hourly basis, we follow a Markov decision process, but it's a specific type of Markov decision process that we have to take care of constraints. We do have a lot of constraints in terms of capacities, shortages, resilience, those sort of things. We'll bring in data analytics So we had developed wind speed prediction. So a combination of physics-based models and machine learning models, solar radiation prediction as well, a combination of climate modeling type of studies and machine learning also. So to have the solar radiation predictions for a whole year, different season. And on that reason, with that respect, we built a minimum. The goal was to minimize daily operational costs. So the assumption is that the system is built. So we're not concerned about CapEx. We're just, this system is given and we want to optimize its minimize its daily operational. There are constraints on power balance, heat balance, cooling balance, and there are constraints in terms on the compressed air energy storage system from the pressure of the air, amount of air that can be stored, amount of power that can be released at any point of time, and with certain state variables that we're going to be observing, like the state of the charge, contribution from renewables, so amount of solar radiation, amount of wind speed, and then the action or decision variables, which all about production levels and charging, discharging decisions. So the Markov decision process was implemented into a reinforcement learning, basically kind of agent approach with a reward function, which means if there are things about meeting the demand, and that means reward, and there would be a safety or penalty function to take care of the constraints. So there would be some hard constraints, the constraint that we cannot violate, and there would be some soft constraint that we could violate. So soft constraints are the one that if, okay, we put a capacity in terms of production, in terms of the discharging from the energy storage system. If we discharge a little bit more, it would be okay. Okay, so at the worst thing, it would be waste, basically. Okay, so these are the type of soft constraint, but there are also hard constraint, which is about capacity of the storage. So the capacity is a hard constraint. We cannot violate it if we cannot store more than that. Okay, so the agent is going to be learning between. So there will be actions, and the agent is going to be in a kind of way of the actor and critic. So the action is going to happen, a reward is going to be generated, the safety is calculated, a state would be updated based on the state of safety and reward, the action is going to be updated. Okay, so that is the way it is done, and using, and this is the way it's been modeled. So on the left, we're going to see the actor network. So the state, whatever is the state of the system is, which are in blue dots, is going to be having the transition into the decisions, the yellow ones, the actions. Okay, and whatever action is happening at any particular stage, which is particular hour, in the next stage, that also be joining the state, the existing state, providing input for the next layer, and that is going to be continuing. So it would be, this transition is going to be done every period. That is what we see at the end in terms of results. So at the left, we do have the way the power system, the electrical system is working in a particular winter day. So it's done for every single day of the year. And for a particular summer day on the right, we see this one. So we could see when the turbine is operational, when which means the compressed energy storage system is discharging, when the compressor is working, which means it is charging, when we are getting energy from the PV, when we are getting energy from the wind, and when we are exchanging with the grid. Okay, and the times that also in a way that basically when the storage is happening, we show it on the kind of negative side. When the consumption is happening, we're showing it on the positive side. And so that and the electrical load is represented by the black figure, and it is managed by the difference between the positive and negative side in order to make sure that, you know, whatever is generated, and if it is generated, if we have too much generation and load is smaller, so there would be storage. If it's the other way around, it will be discharging. So that is done for every single day. And also for the, I should mention that this study, we were not only looking into the power supply electricity for the community, we were looking at the heating and cooling supply as well. So on the left, we have a typical winter day heat balance and how it is basically covered from what sources. And on the right, we have the summer day cooling needs and how it's been basically supplied. So technologies were from heat pump, absorption chiller, and they are joined with the and the boiler for the heating. So there is a gas boiler as a backup when we need heating and storage is not enough. We switch into the gas boiler as the backup last resort. Last study that I want to mention, so we at the first one was at the building scale with 2 different energy storage. The second one was at the community scale with 2 different renewable energy technologies. And this one is at the community scale with combination of one intermittent and one kind of both of them with the kind of stable energy resources. So there is no incorporation of solar, wind type of things. There is the storage plus geothermal and biomass. And this is done for a remote community, off-grid community. That's why we are looking into biomass and geothermal, because those communities are up. They're not connected to roads. They're not connected to electricity grid. They are not connected to natural gas grid. And we need, and even if we incorporate solar and wind capacities in there, because of their intermittent nature, we need to add more kind of stable renewable sources to make sure that they're not going to be staying in the extreme cold without heating and power supply. So biomass and geothermal are explored, especially the case of, so biomass is basically purchased and transferred there, and the way they're doing it through the water bodies. So it goes through, for instance, for Northern Quebec, it goes through Hudson Bay or goes through Labrador Sea. For the geothermal, we were just trying to see what are the potential there, because Northern Quebec is not one of the places that has high potential for geothermal compared to places in Alberta, some places in BC. Okay, so formulation is again a bi-level program. So we do have biomass capacities, and we do have geothermal capacities, and we do have CapEx and OpEx. So the operational and capital models are exchanging with each other, but it's not one capacity. We are trying to coordinate biomass and geothermal. Decision variables for the geothermal technical ones are how deep we go in terms of the wells, how many boreholes going to be there, because based on the number, you're going to have something. But you know, if you put more in there, it will be highly capital intensive, and we might not need it. And the amount of piping lanes, and at the end, how much energy generated from geothermal. Biomass, what fuels, what would be the amount of them from certain different types of fuels, what is the quantity, from where it's coming, distance, and then how much is generated from biomass. Okay, so, and we added one extra objective function taking care of the emissions, because biomass is associated also with emission. Yes, it is. If you put it in the context of biomass decay, and if it's coming from waste resources or residue resources, that is negligible. But there are other types also, and considering that the biomass is coming from a distance, there is the involvement of transportation. So that brings in emissions. So we wanted to take care of the emission function, trying to minimize it. So three objectives. What we call it objectives on surface, which is biomass, objective subsurface, geothermal, and emissions. I think I have maybe a couple more slides. Okay, the constraints, again, we do have heat balance, power balance, energy balance, basically, capacities in terms of biomass and geothermal. So all those decision variables that we were talking about at the CapEx, so number of boreholes, depths, pipes, they're going to be creating their decisions at the CapEx stage. They're going to be creating constraints for the operational stage. And with the operational stage, we are going back into calculating the cost, because the cost is everything, operation and CapEx. And we use a storage of biomass as the energy storage. So how much pellet, wood chips, type of biomass we could store. The amount of stored biomass is basically treated as the energy storage. Data analytics is about load predictions, space heating, and the focus of this study is only on heat. Space heating, hot water. Yeah, okay, so jumping into, so this is the objective functions which are derived based on the characteristics of geothermal and biomass in terms of their heating capacities, lengths of pipes, number of boreholes. So they're all going in there to calculate the cost. And what is happening is that we're going to have a trade-off between geothermal capacity and biomass capacity. So you, at the bottom of this figure, we're going to see biomass scenarios. So HHV, LHV, they are the different materials or types of biomass being used. And the number in front is the distance that is transported, okay? And in that respect, we're going to see when the biomass is coming from shorter distances, like 50 kilometers, even if it's coming from high heat value type materials, because the extent of the biomass available in proximity of northern communities is small, the share of biomass would be higher, okay? And when the distance is going up, it increases the cost for biomass, and that is and that gives a kind of basically boost to the geothermal. And we're looking into something in between, you know, so not going toward compromising the cost by going too much in investing in geothermal, or by investing too much in bringing biomass from longer distances. So something in between is providing the solution, and we characterize that solution. So what type of material, from what distance, what refineries, biomass refineries need to come, and what capacity of geothermal needs to be created. And that would be the basically the cost profile for the system, which is derived based on the kind of, so we do have a multi-objective optimization here. So it is derived based on the kind of Pareto points. And in that respect, we could see the yellow dots are the best values we could get in terms of energy production, and the best values in terms of the cost are the blue line. So they are coming from they are kind of interpreted from the Pareto front. Okay, so that's it, I guess. So I made it to the last slide. And thank you very much for being here and listening to me.